Enthalpy Change experiment from May-June 2015, variant 3.1. In this experiment, you will measure the heat given out by the reaction of excess zinc with copper 2 sulfate solution and use this to estimate the concentration of copper 2 sulfate. The equation is given here. The chemicals listed here are Fa4, which is zinc powder. Fa5 is aqueous copper 2 sulfate solution whose concentration is to be estimated. Chemicals and the apparatus given here are Fa4 in a test tube with a rubber bung. It's zinc powder. Then Fa5 copper 2 sulfate solution, and then 50 centimeter cube measuring cylinder, 250 centimeter cube beaker, and a plastic cup with a thermometer. Method: read through the instructions carefully and prepare a table below for your results before starting any practical work. So here they have given us a space where a table is to be drawn. So this is the space here, and then next part starts from here. So what is to be included in the table? Let's read this now. Support the plastic cup in the 250 centimeter cube beaker. Use the 50 centimeter cube measuring cylinder to transfer 40 centimeter cube of Fa5 into the plastic cup. Measure and record the initial temperature of the solution in the plastic cup. So first thing to record here is the initial temperature. Start the stopwatch, measure and record the temperature of the solution every 30 seconds up to and including the temperature at 2 minutes. Stir the solution frequently. So here we have to take observations of temperature every 30 seconds up to 2 minutes. It means initial, then half minute, then first, then 1.5 and 2. So altogether we have 5 observations of temperature till 2 minutes. Then at time 2.5 minutes, add all the powdered zinc to the solution in the plastic cup and stir the mixture. Record the temperature every 30 seconds from 3 minutes up to and including T 9 minutes. Stir the solution constantly. Now, let's make a table where we will record that we have to observe our solution every 30 seconds up to 9 minutes. So let's prepare the table first. Here I have made a table in which I have recorded all the times in 30 seconds interval. However, I have crossed out this 2.5 minute. Why? Because they have asked you to record the temperature till 2 minutes, and then after adding all the powdered zinc at 2.5 minutes, you have to record the temperature from 3 minutes. So temperature of 2-minute recording and temperature of 3 minutes recording should be taken. 2.5 minute recording must not be observed. Therefore, it is crossed out. Now let's start this experiment. Now support the plastic cup in 250 centimeter cube beaker. Use the 50 centimeter cube measuring cylinder to transfer 40 centimeter cube of Fa5 into the cup. We will support this plastic cup in this 250 centimeter cube beaker. Now we will transfer this Fa5 40 centimeter cube in this 50 centimeter cube measuring cylinder. So this is 40 centimeter cube Fa5 solution. We will transfer this in this plastic cup. Now the next point says measure and record the initial temperature of the solution and start the stopwatch. Measure and record the temperature of the solution every 30 seconds up to and including the temperature at 2 minutes. And we will record all these observations of temperature here. Now let's record the initial temperature at 0 minute. While recording the temperature in the thermometer, if we look at the graduations, the smallest graduation, that means least count of this thermometer, is 1 degree Celsius. Therefore, we need to record all of our temperature values up to the 1 decimal place, that's either ending at 0.0 or at 0.5, because we have to observe up till the error of the device, and here is the error, which is half of the degree. Therefore, the initial temperature here is 26.0. Now, let us start the stopwatch, and every 30 seconds, we will observe this temperature. Now at 30 seconds, it's again 26.0. Now at 1 minute, again, it's 26.0. At 1.5 minute, again, it's 26.0. At 2 minutes, again, it's 26.0. Ideally, when we haven't added anything, the temperature will not change. Now, at 2.5 minutes, we will add all of this Fa4. So at 2.5 minutes, we will add all of this Fa4. Now this is 2.5 minutes. We have added, and they have said stir continuously. So let's stir and record the temperature from 3 minutes. Now at 3 minutes, the temperature is 36.0. At 3.5, it's 39.0. At 4, it's 41.0. The temperature rise is not increasing as much now. At 4.5 minutes, it's 42.0. At 5 minutes, it's 43.0. Now it's 44.0. Now at 6, it's not exactly 45, so we will take it as 44.5. 44.5. It's 45 at 6.5 minutes. At 7, it's 45.0. Temperature is not increasing anymore. At 7.5, it's again 45.0. At 8, it's 45.0. Temperature is not rising anymore. It means the reaction has been over. The content will cool down gradually now. Therefore, the temperature is not rising anymore. Anyways, 2 more observations to take. At 8:30, it's decreasing a bit from 45, so it's 44.5. Now at 9, again, it's so we have taken all the temperature readings. Now let's move on to the next part where it says on the grid opposite plot the temperature on y-axis against the time on x-axis. The scale for the temperature axis must allow you to plot a point with a temperature 5 degrees Celsius greater than the maximum temperature you have recorded. The maximum temperature in our temperature readings is 45 degrees Celsius. So 5 degrees above means we have to select a scale for the graph which must allow us to plot at least 50 degrees Celsius. That is 5 degree above our maximum temperature. And on x-axis, we can plot easily the time, which is 0 to 9 minutes every half minute. And then we will draw as best fit straight lines on the graph as they have said here. So first of all, we need to plot this graph. So the graph we have here, I have written here time on x-axis and temperature on y-axis. In order to select the scale, we need to be very careful about these graph questions because they penalize if you select such a small scale that will cover only half or less than half of your graph paper. Therefore, we need to scatter our values as much as we can. So we need to take a bigger graph scale to incorporate all the time values from 0 to 9 minutes and the temperature. If it is going up till 50 degrees Celsius, then we must not start with a 0 because from 0 to the minimum temperature, which is 26, the graph will be empty. So 0 to 26, if we take in here from 0 to 26 somewhere here, if we take this portion will remain vacant. Therefore, we will not select our scale that is starting from 0. So we will take false origin from here. So we will start with the 25 degrees Celsius or 26 degrees Celsius minimum. So let me select the scale now. I have selected a scale on x-axis that is giving me a full range of 9 minutes starting from 0. But on y-axis, I have started from 25 so that every 20 boxes I have taken 5 degree. So I will reach a maximum of 50 degree with 70 to 75% of the graph covered. Now, let me plot these values on the graph. This is how the graph is plotted. Now, let's read the points to draw the straight lines here. Here they have said you have to draw these best fit straight lines. Number one, a line through the points between t0 minutes to t2 minutes. So one of the line will be a straight line from 0 to 2 minutes, and it's clearly here 0 to 2 minutes. It will be a straight horizontal line. And then a line through the points between time 5 minutes and time 9 minutes. Now here we have from this time 5 minutes to 9 minutes, we have a bit scattered graph here. Now let me tell you how to draw a best fit straight line on these points. Now, if you look at the lines I have drawn here, I have possibly drawn 3 lines. Number one is the horizontal line here, and then a straight line like this, incorporating these 2 points, and then I have drawn one dark line like this. So out of these three, which one is the line for best fit in my graph is the line I have drawn in dark color. Why? Because if I show you the time, here is the 5 minute, and if we go here 5 minutes, so here we have 1, 2, and 3 points mainly remaining below the line, and here we have 1, 2, and that third point remaining above the straight line. So this is the line of best fit in our case. Now let's proceed on to the next straight line, which says a vertical line at time 2.5 minutes. So let's draw a line, a vertical straight line at 2.5 minutes. So this is our vertical line at 2.5 minutes. Now the next part says extrapolate the first two straight lines so that they intersect the vertical line at time 2.5 minutes. Use these extrapolated lines to determine the theoretical temperature change at the time 2.5 minutes. So let's extrapolate these two lines. This line extrapolated here, and this line is already extrapolated, so it's crossing already. Now the 2.5 minute crossing line shows the theoretical initial temperature at 26 degrees Celsius, and the theoretical final temperature here is 46.5. So we will take out the difference of these two readings to get the change in temperature here. So the change in temperature is recorded here as 20.5. This was the rise in temperature theoretically at 2.5 minutes. Now let's proceed on to the next part after this graph. In the next part, they have asked you to show your working and appropriate significant figures in the final answer to each step in your calculations. Significant figures appropriate. It means minimum you have to take 3 significant figures, and for better calculation you can take 4 significant figures. Now the next part says use your answer to B3 to calculate the heat energy produced in the reaction. So the formula for energy we have studied is E is equals to mc delta T, where m is the mass of solution, mass of water ideally, which is from the solution, and multiplied by the specific heat capacity of water. Specific heat capacity of water is a constant value, which is given here as 4.2. Then delta T is our change in temperature, which we have calculated previously. So in this case, the mass of aqueous solution was actually on the previous part, which is aqueous phase is just copper sulfate. And we have taken this copper sulfate Fa5 as 40 centimeter cube. So the mass of solution means mass of water taken here will be 40 multiply 4.2 is specific heat capacity given, and then the temperature change, which we have previously calculated as 20.5. So the delta T here is 20.5. So if we multiply all these values, I will get 3,444 joules of energy. Now the next part says the molar enthalpy change for the reaction shown below is minus exothermic 2.219 kilojoules per mole. Use this value and your answer to part 1 to calculate the number of moles of copper 2 sulfate in your reaction. Now the formula of enthalpy change we have studied is delta H is equals to E, amount of energy released, which must be taken as negative because it was released, divided by 1000 to make it in kilojoules and multiply by the number of moles of limiting reactant. Now, delta H given in this question is minus 219 kilojoules per mole. So delta H here is minus 219 kilojoules per mole, which is equals to the energy in negative sign means exothermic, and the value for energy here is 3444 divided by this 1000 to make it in kilojoules, multiply by the number of moles which needs to be calculated. So in this case, the calculation of moles will bring you the answer 0.0157 moles in three significant figures. The next part says use your answer to calculate the concentration of copper 2 sulfate in moles per dm cube in Fa5. So the formula of concentration we have studied is concentration in moles per dm cube is equals to the amount in moles divided by the volume in decimeter cube. So in this case, the concentration can be calculated by using these formula. Moles are 0.0157 divided by the volume of Fa5, which we have taken previously as 40 centimeter cube of Fa5 was taken. Therefore, we will take the volume here as 40. It was in centimeter cube, so divided by 1000 to make it in decimeter cube. And the answer for this calculation of concentration is 0.3925 moles per dm cube. The next part says calculate the maximum percentage error in the highest temperature that you recorded in your results table. Now, the maximum temperature recorded in the previous table was actually 45, which was consistent from 6.5 minutes till 8 minutes. So this was the maximum temperature we have recorded. Now, if we are using just one temperature to find the percentage error, we will take the error just one time. So the least count divided by 2, which means the error of our thermometer was 1 degree thermometer was given. So divided by 2, we will get plus minus 0.5 degrees Celsius as the error for the thermometer. Now, if we want to calculate the percentage error, what we do, we take the error in our value divided by the measured value. And for percentage, we multiply by 100. So in this case, what we have taken error just once. Why? Because we have just taken the highest temperature, the one-time reading. So it was 0.5 just one time divided by the maximum temperature we have recorded was 45. Multiply by 100, it means the percentage error of the highest temperature. And it is here in this case 1.11. Now the next part says D2. A student suggested that the concentration of copper 2 sulfate could be determined more accurately if a greater mass of zinc had been used. Explain whether you agree to this student. Now, according to the formula, the student is right. According to the formula, if the measured value here in any of the percentage error formula, if measured value is greater, and here they have said greater mass of zinc used. So if this value increases, the percentage error decreases. It means the value gets more accurate. However, in our calculation, in this experiment, what has happened, the zinc which was used was actually used here in the question. They have said the zinc was in excess. So if we have already something excess and we measure its mass more accurately, it doesn't really matter. It doesn't really change the accuracy of the experiment. So we disagree with the student. And the reason why we disagree is since zinc is used in excess. The next part says a second student suggested that the concentration of copper 2 sulfate could be determined more accurately if a smaller volume of copper 2 sulfate was used. Explain whether you agree with this student. Now, if we look at the same formula of percentage error, and here they have said the concentration could be determined more accurately if a smaller volume of copper 2 sulfate used. So if the measured value, which is the volume of copper 2 sulfate is smaller, if this value gets lower, the percentage error will increase in the experiment. And copper sulfate was not excessive reactant in this reaction. Therefore, we need to disagree. Why? Because a smaller volume of copper 2 sulfate solution will give bigger percentage error. In this way, we comes to an end of 15 marks enthalpy change question from May-June 15 variant 3.1.